a very special case of this, namely where u2q was just half q squared plus r, and this u4 was just u, a constant. Okay, so and then we had, so our Hamiltonian had two parameters, r and u, and we wrote down a recursion relation for that, which I will just summarize here. And u prime okay, and I remind you that we also got a fixed point and what I did last time was to say, let's suppose we generalize this discussion by adding other operators to the Hamiltonian. Okay, what are the other operators you can add? So these are called irrelevant operators. And I gave an example last time, so let me just, so we said that we can modify this thing by adding some extra p's, which I call, I think, v2 q squared, and remember that the coefficient of q squared has been normalized to half. Well, actually there's a half there, so I don't need the half here, sorry, so we erase that half. Coefficient of q squared in this is 1, so it's half here, and that is always fixed by a normalization of the renormalization of the sigma. So anything that comes here will now necessarily have higher powers of q squared. Okay, so this is like an expansion in powers of q squared. So this has to start at order q fourth. So generically it will be q fourth plus maybe q sixth and so on. So what do these things correspond to in position space? They correspond to higher derivative operators. So if this corresponds to the operator box, this corresponds to box squared, and this is box cubed, and so on. So in principle, your Hamiltonian could have terms involving higher derivatives. So in position space, this term corresponds to, let's say, d sigma, or I can write it as sigma box sigma. Then this would correspond to sigma box squared sigma. And the interesting feature about all these things is that as if you calculate the naive dimension, the dimension of this operator, it is more than this or this, because this has 4 momenta in this, so that's already 4. And then there's the dimension associated with sigma, which is there anyway here. So this term has dimension 2 more than this one. This term has dimension 2 more than this one. So you're writing terms with higher dimension in momentum dimension, energy dimensions. And in principle, there are an infinite number of them. Okay. Similarly, this U4 can have Q dependence. We've started with a simple case where it doesn't. And if you introduce derivatives, powers of Q in this, you will effectively be adding operators to the Hamiltonian which have higher dimension. So as you can imagine, these are an infinite number of possibilities of higher dimensional operators. So that's why these irrelevant operators are an infinite number. And so we should at least consider what happens when you add these, and is it consistent to just keep this? In particular, is the fixed point structure change? The fixed point change a lot? And the way we control the effect of these things is by this parameter epsilon. So we have to argue now that this is not affected to this order in epsilon, and all corrections that are going to come are necessarily higher order in epsilon. Okay, and that's what we started doing. And simple arguments, we started out by saying that this thing most likely is of order epsilon squared. And the way we did that, if you remember, was to look at the diagrams. The diagrams to lowest order in the parameter u is just this one, where there's u, and then there's this with with these things closing. So this is a diagram that can at the most contribute to the existing diagram, which can contribute to sigma 4 with the constant u, and this can contribute to sigma squared, and we've already taken these into account in calculating this. Okay, so to order epsilon, all diagrams have already been taken care of. So this correction cannot be of order epsilon simply because there is nothing else at order epsilon. So it has to come at higher order. So your operator W2 must necessarily be of order epsilon squared or more. Okay, that was a starting point, and what we have to do is to verify this, is that this assumption is consistent, and see if you can check that the fixed point is not affected. So to that effect, we wrote down the equation. So remember the RG equation, starting with this Hamiltonian. I'll write it down again, so I'll just summarize. So your new thing. So these are the terms that were already there. So this is the rescaled momentum. Remember, we've integrated out half the momenta. You're left with things with the lower momentum. So that's this. Plus, these come from graphs which are of this. These come from the graphs which are of this type. Okay. So it's so what is this? So this external momentum again is q by 2, and this internal momentum is p. So this comes from a vertex which has q by 2, p, like that, where this is closed. So the u, this u here has these 4 momenta. So that's what I've written here. So it's the u4 q by 2 minus q by 2 p minus p by u2p plus higher orders. And I won't write down the equation. Similarly, we had an equation for u4 prime, which you can check in your notes, which involved diagrams like this. So this is a correction to the 4 sigma interaction, and we had something like this, which I won't bother to write down. Okay. So our fixed point, we're going to assume. So now remember that we're solving not for fixed point as numbers, but fixed points as functions. So we want u2 star as a function of q. So the fixed point will be where the left-hand side function is the same as this u function here. So you have a set of functions which you plug in on both sides, and they should satisfy it identically. So it's actually an infinite number of coupled equations, functional equations, because they're all functionals of they involve products of functions and integrals over the momenta and so on. So it's a complicated thing, and we've simplified it to this simple algebraic equation. We're just checking that. So the fixed point solution to leading order, we expect then is of this. This is our original solution plus some correction, which I want to verify, and u4 star q1 q4 we say is u star, which is of order epsilon, plus order epsilon squared. This is order epsilon, this is order epsilon. Okay. So we will assume, and this order epsilon squared thing now I will assume is, there's a razor. So let's call it v2q squared, and where v2q squared, I've written it somewhere, starts off as, so I'll just write here, where some w, what have I called it, w1 q fourth plus w2 q sixth and so on. Okay. So these are the relevant operators. And then I want to verify the consistency. So let's put this into the recursion relation. So what are we going to get? So we're going to get, so we have to estimate this now. This is just going to be that. What is this going to be? To leading order, I'll just write this as our original calculation, 12 U star R star. This was our leading order estimate for this, plus correction. What can this correction be? Well, it can be correction from the numerator or from the denominator. The numerator correction we said is of order epsilon squared, because at order epsilon we already have the fixed point. So necessarily this correction, this whole thing that you left out of this must be of order epsilon squared. That much is clear, because the order epsilon part we've taken into account. So we'll give it a name and call it call this thing epsilon squared times some f2 of q squared. So I separate out the epsilon squared, because I want to check if it's consistent, and I'm going to put that in here. Okay? And then write down the recursion relation. So what's the recursion relation going to give me? So we put this on the left hand side, on the right hand side. Remember that this factor is 4, because we chose it to make that coefficient q squared. So your recursion relation, this is what I wrote down last time, is v2 star q is 4 times v2 star q by 2 plus epsilon squared times f2 q. Okay, this is at the fixed point, so you can call it f2 star if you want. So we have to get this solution. This solution is not hard to do. You can solve it by iteration. The reason is, as I said, this starts off as q fourth. So because there are 4 powers of 2, it's q fourth by 16, so it's actually 1/4. Okay? So this is actually a small correction. So you can start off by putting in this and putting it back in as many times as you want. So you get, so v2 star q to lowest order will be just epsilon squared f2, lowest order. Next order, you put this into that, and then you'll get v2 star q will be 4 epsilon squared f2 q by 2. Next order, you get that. If you put this into that, and you keep doing this, and you will get the sum over n. Two to the power of 2n you can easily see that each iteration does that. You get a power of 2 from this, and the inside q is divided, and you get a series like that. Okay? And this thing again starts off as q to the power of 4. So this goes as 2 to the power of minus 4n q fourth. Okay. So because of this 2 to the 2n, 2 to the minus 4n, this goes as 2 to the power of minus 2n times q fourth, sum over, get something like that. Clearly this is a convergent sum. It's convergent because it's 1/4, 1/16, so on. So this is a convergent sum, and this is a crucial point. Because of this, the nature of the perturbation, the fact that it starts off as q fourth, the fact that you get 1/4 every time, it's getting smaller and smaller and smaller, this sum converges. So this iteration you can consistently do and get a finite answer. So that means this procedure of assuming it's epsilon squared small correction, sorry?
Can you explain this?
This one? This one? Oh, I just repeat. So I just repeat it. Repeat n times. So now you put this back into that. Okay, so the first term, if you put this into that, you'll get q will become q by 4, and then there will be a 4 and 4, so 16. Yeah, this v q squared always starts off as q4. That's the crucial point. Okay, so v is just f with an epsilon squared factored out, and this fq starts off as q to the power of 4. That's the crucial point. So because of this power of 2 here, it gets smaller with each iteration. So, so just to emphasize this point, let me remind you that the reason this became bigger, what was the reason for this factor of 4? It's because of the dimension of this object as a mass squared. The reason this was roughly the same was because it's an almost dimensionless object, this coupling constant. These guys have dimension, because this have positive dimensions of mass, this has negative dimensions of mass. So when you do the iteration, it gets smaller each time. That's the nature of the irrelevant variable, and that's what's bringing in this convergent factor. So when you have irrelevant variables, they're always accompanied by these convergent factors, and you can just iterate and sum. So the contribution from n iterations does not diverge, it converges. Effectively, with each iteration, the effect of your term becomes smaller and smaller and smaller. So that's why it converges. And you get a finite answer, and it's order epsilon squared. So our assumption is consistent, namely that this correction is indeed of order epsilon squared. And if you remember, one of the criterion we had was that the correction should be of order epsilon squared in this equation, then it's consistent. And here it should not occur linearly. And that also you can check when you look at this equation, which I'm not doing, which is another analysis. But you can easily see that here this actually you can see it very easily because there are two propagators, and here, and this thing occurs in the denominator. You can show that there will be no correction here to order epsilon squared, but it will be a higher order in epsilon. Okay? So this is a analysis that you have to do, the same kind of analysis that I did for this equation. You have to do for this equation. It's not very hard. You just look at the diagrams and you show that the first correction is necessarily higher order. So I've shown you that this equation is not affected. It's a self-consistent way. And in the same way, you can show that this one is not affected. Okay? Yeah, actually it's fairly easy to show because this correction shows up in this equation in the propagator. It's a 1 over epsilon squared correction in the propagator. This whole diagram is already of order epsilon squared. So when you bring out that power of epsilon squared, you get an order epsilon fourth correction. So this equation is only affected to order epsilon fourth. So you've consistently shown that this term does not affect your fixed point solution. Okay? And then now you look at the scaling of this, and you see that W1 prime you can easily check is 1 by 4 W1, W2 prime is 1 by 16 W2, and so on. This is the leading recursion. So these are the crucial, these things just follow from dimensional analysis, and that's why they're called irrelevant variables in this sense, but you always have to actually be careful and show that these irrelevant variables are indeed irrelevant for the purposes of this fixed point location. Okay? So why are we doing this analysis? Because we want to convince ourselves that even if you consider the full Hamiltonian, which is all enormous, there is a consistent or epsilon expansion you can do such that the leading one is just this, has all the properties that you want, that you're going to study, and then corrections of order epsilon squared and epsilon cubed and all, which is the effect of all the irrelevant variables. So the moral is the relevant, these are called relevant and marginal variables are the ones you analyze first. The irrelevant variables are usually corrections to that, which which are in some sense the finer structure of the RG, which don't affect the main main conclusions about the location of the fixed point, etc. Okay. Okay, so that was just to complete the analysis of this Hamiltonian. Any questions about this analysis before I go on? So now you understand the idea of irrelevant operators, and I said there are lots more of them than relevant ones, and that's why they're important. The other thing is a matter of terminology. This object is called the Wilson action. And what RG studies is the flow of this Wilson action, and what we have here is in some sense an exact flow equation that tells you how the full Hamiltonian flows, not just some 2 parameters. Okay, and later on when we do well, maybe in a couple of lectures we'll talk about a different version of the RG where we study the whole thing more exactly. 4. Yeah, yeah. Or 4 minus d, 4 minus d, yeah. Epsilon is of order 1, yeah. So people have done numerical studies. It works. Oh, because, why does it work? That's a good question. Well, it's like saying the electric charge is 0.3. Why does it work? The point is,
You are ignoring higher order terms based on assuming epsilon is not there.
no. So, well, the question is what precisely occurs along with 0.3, right? So if the powers of epsilon, if the powers that multiply epsilon are small enough, so for instance, if you look at the calculation, I think I mentioned it that the anomalous dimension comes out as something like that. This is 2-loop calculation.
Not only epsilon, something going along with epsilon, which makes it small.
Okay, well, so there are 2 issues. One is the formal issue of doing the epsilon expansion, which you can do as, in fact, there's a famous paper by Wilson says QFT in 3.99 dimensions. So there epsilon is 0.01. That's fine. So the question, for a practical application, you want to take epsilon equals 1. Then the absolute actual value of these coefficients will matter.
I believe there's still a debate going on why it works.
It's not a convergence scheme. It's at best an asymptotic convergence, asymptotic series.
Even when epsilon is far less than 1, it's still an asymptotic series.
Yes, it's always an asymptotic series.
But whether an expansion like that is valid or not.
So yeah, but I think people have done Borel sums and things and found reasonable results. And numerically also, it agrees with, but that's the nature of all these problems anyway. You never have unless you can prove rigorous theorems, you have to take it as an experimental fact that it works. It agrees with numerical works. Yeah, so now, yes, so if accepting the limitations of the epsilon expansion, but of course for the purposes of this, for Wilson's, apart from actual calculations, the whole point was to show the structure of the RG, and for that it's a very good tool. But now I want to talk about one more thing. Having got the scheme, what do you do with it? Okay. Yes?
So in field theory textbooks, we use dimension regularization.
Yes.
There it is just a regulate.
Yes, yes.
Here you are
No, here it's a parameter.
you are using it as an
This is expansion parameter, yeah. It's more like 1 over n.
Right.
1 over n in QCD with n equals 3. Something like that, yeah. Yeah. So it's just here is just a parameter. So what do you do with the RG? Well, you got this fixed point structure. We got some exponent. Yes. Go ahead.
So in diamond regularization,
Yes.
whether it works or not depends on whether you're talking about bosons or fermions. For bosons, you have to go less than 4. For fermions, you have to go greater than. So there's some
In dimension regularization. No, I don't think there's anything like that here. Well, dimensional regularization, okay, with fermions if you're worried about chirality, but otherwise, okay, there's some issues about chirality with fermions, right? Okay, I won't get into that here. Okay, so I want to talk about what do you do with this. And the obvious thing is, obvious application. After all, what are you trying to do? You're trying to solve for correlation functions. And I'm going to give you a simple example of how this is used to calculate correlation functions, or at least estimate scale dependence of correlation functions. So scaling property So this will be like a practical application of this. This kind of thing is done. We're going to do it in this example in the context of critical phenomena. But exactly the same thing is done for quantum field theory, where you calculate Green's functions in QCD. RG techniques are used to estimate correlation functions. And there's a fairly detailed argument given in this review article by Wilson and Kogut, which deals with calculating correlation functions when t is close to Tc. It's a little elaborate, the argument, and it's easy to get confused. So I'm going to take a simpler version of his argument, where he talks about not close to Tc, but t almost equal to Tc. So neglect the fact that t is different from Tc. And the difference is mainly technical, but you get stronger results. But before I talk about the correlation function, I want to talk a little bit about the logic of how you use the RG for this, because this illustrates the calculation. Okay. So I'm going to talk a little bit about the flow and how RG is used. So I'll remind you about this diagram we had. So we had a fixed point here, and then we had one condition for the recursion. There was a recursion relation, and then we said if you satisfy a linear relation between R and U, you will lie on the critical surface. One term is 0, the growing eigenvalue is 0, and you're left with the falling eigenvalue, and you're on the critical surface, and you flow towards the fixed point, iterate to the fixed point. And then we said if you're a little bit away, a little bit away from the fixed point, you expect a situation where you get things that are proportional to t minus Tc. Initially, it gets closer to the fixed point, but then it starts to diverge, because what happens is that the growing term is not exactly 0. It's small, but not 0. The shrinking term initially shrinks, but at some point, the growing term starts to really take over, and then you take off. Okay? And you can draw many of these curves and take them arbitrarily close to the critical surface, and eventually you'll get a curve like this, which is the limit of this, which effectively starts from the fixed point and goes off like that. This curve is called the renormalized trajectory. So this is your fixed point. Okay. So at this point, I should point out one more thing, that our fixed point. Let me write down those equations. R prime was 4R, wait, where is the equation? R plus 3cu by 1 plus r, and u prime is 2 to the power of epsilon u minus 9cu squared by 1 plus r squared. And we have two fixed, I'll just write this down, u 1 by 9c epsilon log 2 . Okay, this is the fixed point we're talking about here. There's another fixed point, which is that there's one more fixed point in this theory. Does anyone know what that is? Huh? Gaussian fixed point. U is 0, R is 0. That's over, if you want, over here in this figure. But there's one difference between those two fixed points. Here, if epsilon is positive, this number is u prime is greater than u for the Gaussian fixed point, r prime is greater than r. So both of them are increasing. So you have two increasing eigenvalues. Whereas this fixed point we found one increasing, one decreasing. Okay, so there's a difference in nature. In general, you can also show that if you start from this fixed point and you can tune your temperature to be on the critical temperature for this, which effectively says essentially R is 0. But then this increases, and there is a trajectory that flows to this fixed point. So you can have a trajectory that flows from the Gaussian fixed point to the Wilson-Fisher fixed point. Okay? So and that in particular can lie along the critical surface. So I'm just going to mention that because later on, because right now I'm talking about flows, and later on we'll talk about flows between fixed points. So I just wanted to mention that point. But here we are just talking about this fixed point, and where it goes to after that is essentially unknown. We don't know where it goes. So, but certainly it's going to go into some theory where probably the correlation length is 0. Okay? So here the correlation length is infinite. Now what is the nature of this flow? So initially you start with some u0 and you iterate, and it gets closer to this critical surface. Now once you're near this region, by the way, it spends a lot of time in this region because each iteration reduces it by a factor of, let's say, 2 or some factor, but it's logarithmic. So the time it spends before it gets to the fixed point is actually infinite. So it spends a lot of time in this region. Okay? So initially, whatever your initial Hamiltonian may be, at some point it starts to approach the fixed point value, or fixed point value modulo the variable that's getting smaller in this direction. So the relevant variable has been tuned to the critical value, which is fixed, and the other one starts to get smaller. And so it spends a lot of time in this region, and then it starts to diverge. So there are 3 regions you have to analyze. One is the early region, where it has memory of your initial Hamiltonian. This is what they call the transient region. Then there's a region where it's more or less constant, where in this region you can predict its properties because it's essentially governed by this. It's spending most of the time near the H star. And then there's a region where it goes off. What happens in this region is the relevant variable is becoming significant. What does that mean in terms of correlation length? That means your correlation length is becoming of order 1 in your units, of the order of the lattice. Okay? So this region is called the correlation length. So I shouldn't say this region, over here, correlation length region. This is the transient region. And this is where things are simplest. So you will find plots like this, where this is some Hamiltonian, some term in the Hamiltonian, and this is some iterations. So you have some u0, which goes to some fixed point value, or u naught or r naught, which goes to some fixed point value, some parameter, and then it starts to take off. So this is called the correlation region. So then it takes off like that. Okay. How do you, oh, what's happening? The correlation length is initially you have some Hamiltonian which has a very large correlation length because you tuned it to be near the critical value, so it's 1000. At that point, the value of r is very small. With each iteration, r is getting bigger, 4 times by a factor of 4. So the correlation is getting smaller and smaller and smaller. So when that 1000 becomes of order 1, then the growing eigenvalue is starting to become big, that means. That means r has become large. That's when it starts to dominate. Okay? So that means in physical terms, when you're talking about length scales, so in field theory, if you're talking about length scales of the order of the mass of the particle, then the mass becomes important. If you're at high energies, the mass is not important. So this is a region where, so mass here is like the deviation from criticality. Okay? So when your deviation from criticality is small, you can do a large number of blockings before that becomes significant. So I'll write down an equation in a minute. So over here, you've done enough blocking that whatever, see, however large it started off has reduced to 1. If it were exactly 0, of course, it would always, I mean, if C were exactly infinite, it would remain infinite. But if it's large, it keeps decreasing, and around here, when it starts to take off, that becomes of order 1. Well, so I'll write down an expression for that in a minute. So this picture you have to keep in mind. And okay, so what are we going to do here? We're going to start with some Hamiltonian here, which we don't know how to calculate with this Hamiltonian. But make sure it's near the TC. Then you just apply the blocking a large number of times, and you get the Hamiltonian in this region. In this region, the Hamiltonian is a fixed point Hamiltonian. So you calculate your correlations with that Hamiltonian. Okay? And the correlations here and the correlations here are related by a very simple scale transformation. You can work, that's what we're going to work out. So if you calculate the correlation using this Hamiltonian, work backwards and get the correlation with this Hamiltonian. Okay? So the idea of the RG is this. You keep blocking till you're in this region and do the calculation there where you know what to do. Okay? So this step has to be made precise. Now, depending on whether you're exactly on this and you're going there, or whether you're going off, will bring in different shades of approximations. If you're going here, then you're on much firmer ground. You can just use H star, the fixed point. If you're a little bit off, you have to be a little more careful in using it. Okay? So let me write down the expression. At this point, we have to do one thing, which is become continuous. Change the discrete notation to continuous notation. What do I mean by that? What I mean is, so far we've been blocking and taking lambda to lambda by 2. So we say the cutoff, instead of 1, you make it half, integrate out. This is discrete. But instead of that, change it lambda to lambda minus d lambda. Just take out a small slice of the momentum. Okay? So in other words, you integrate out lambda minus d lambda less than p less than lambda. Instead of here you are doing lambda by 2 less than p less than lambda. So do that. And then do this an infinite number of times. So you get a continuous transformation. Okay? So what happens, so you can because you're doing it continuously, you can introduce a parameter, continuous variable, which you can call t, such that if your lambda was your initial cutoff, after time t, the cutoff is lambda e to the power minus t. So this process of reducing the cutoff infinitesimally, but over an infinite number of times, you parameterize it by a variable t, so that after time t, your cutoff is lambda e to the power minus t. So t equals 0 to your original theory, and then you evolve in time. So this is some kind of a time variable. It tells you how to evolve. And previously we had a recursion relation. We had HL plus 1 as some operator on HL. That is what this was. So L, so here L is the number of iterations, how far you've gone. Instead of that, we have a continuous variable t, which tells you how far you've gone. And instead of this, you will have a differential equation which says dh, so we'll parameterize it by t. Okay. So instead of doing, so the idea is simple. Instead of doing it in a discrete step, you do it in an infinitesimal step and write down a differential equation instead of a difference equation. Mathematically, you can always do that. Note that this operation u on HL did not depend on L. Okay, whether you did it the first time or the second time or the third time, the relation was the same. So there's no L dependence here. In the same way, there is no explicit T dependence here. Okay, so there is a time translational invariance. Just a word. But I mean, you can use your intuition to, you can think of this as a flow, something flowing. Okay? It's just a word. Okay, so what happens to the correlation length? So the correlation length was C at t equals 0. What is it at C of t? What's the connection? Remember, the correlation length is physically the same. All that's changing is your unit. And your unit has become longer by a factor e to the power of t. The length has become larger by a factor e to the power of t. So the correlation length is going to become smaller by a factor of t. So this guy will be bigger than that by this factor. Right? So as t progresses, or so you can invert this, say C of t is e to the power of minus t. So the correlation length keeps reducing like that. This, of course, gives you equations for the various couplings. So dut by dt, drt by dt, etc. Everything will now be labeled by t. It gives you a flow. So what is the form of the flow? We've seen that. Okay, let's first look at what is the shape of this curve. This is the growing eigenvalue. Okay, and we saw that it has a behavior. So H. So if I call this Hamiltonian HST, this is a solution of your RG flow. So HST satisfies that equation. Okay, with initial condition that it starts from the fixed point. And you perturb it a little bit and see how it goes. What we did in the linearized analysis tells me how this behaves for t where it's near the fixed point. And we know that it does something like this. So this is the deviation from the fixed point. And it grows as a positive power of t. Because remember, there was a factor of lambda 1 which is close to 4, and it was each iteration it got multiplied by lambda. So the continuous version of that is this growth factor. Okay. But actually, if you're imagining these trajectories, okay, we also saw that it has a form. There's a coefficient multiplying it, which says the deviation decreases with t minus tc. Okay? So in other words, it's of the form, so I'll write it here. So I can write ht in the following form, is h star plus, I'll factor out the t minus tc and then write, in other words, when t equals tc, there is no growth. If you're exactly at tc, the growing eigenvalue is not there. When t is slightly away from tc, it has this form. If you remember, this was a form we had in the iteration. We had a factor, some lambda 1 to the power of n times some product of v11 and so on. And we said that this thing has to be 0 when t equals tc. Otherwise, it's proportional to t minus tc. Okay? So with each iteration, there's a factor lambda to the power of n times a factor which depends on t minus tc. That was how the eigenvalue was growing. So it roughly has that behavior. Okay? So initially, this curve has to match on with that curve. Later on, the linear approximation will break down, but there will be some exact solution. Okay, so no. What I'm saying is there is an exact solution here, which you can solve for, which is this curve. Right? The linearized approximation is what we've done. So the exact solution has to agree with the linearized approximation for t near that region. Okay, so so what do you expect for this A? Of course, it's related to this eigenvalue lambda, and the way you can see it is the same way that, well, let's put it this way. When t minus tc times e to the power of at is of order 1, this is the criterion for what is called the correlation length region, where when c of t is of order 1 by definition, right? So so what is this? So this is t minus, and this is therefore, so c of t is like e to the power of minus t. So t minus tc times e to, so t minus tc times, so your initial correlation length is therefore e to, so let t be the time at which this happens. That means your initial correlation length must have been e to the power of t. Okay? The longer you have to wait for this to happen, the larger your initial correlation length. So c is of order e to the power of t. So this is c to the power of a, so order 1. So that means c goes like 1 by t minus tc to the power of 1 over a. Okay? But we know that this has to go as 1 over t minus tc to the power of nu. So basically a is 1 over nu. This follows from this, but this result we already know. That's the definition of the exponent nu. So that means this a must be 1 over nu. So this is 1 over nu. So your behavior is h star plus t minus tc e to the power of t over nu times ht. This is the same argument we've been using again and again to get the correlation length. This exponent nu has to do with that rate of growth lambda. Okay. Of course, and as before, you can see that bringing t closer to tc can be compensated by a change in t. So this factor is effectively, what is it doing? It's just shifting your time, how long you've been. So if you start with a given t and go a certain this time t, and you start with a closer to critical temperature, then you have to go to a later time to get the same value. So you can approximate this by some e to the power of minus t naught by nu, some define a t naught like that, and write this as h star plus e to the power of t minus t naught by nu times hd. It's just another way of writing it. So the information about how far you are from criticality is in this number t naught. Okay, and of course this will be a function of t. So I've just rewritten my flow by saying t minus tc tells me when this thing becomes of order 1. So when t equals t naught, this is of order 1. Okay, so that defines my t naught. Sorry. So in other words, so we know the shape of this curve. It has that form at least near this region. And in the linearized regime, when it's nonlinear, you have to solve the actual RG and get that solution. But the fact that the property like time translational invariance of the equations, etc., continue to hold. So you can conclude that the entire effect of changing Tc is to just shift this curve. So let's look at this curve. This is a point where T naught happens. Okay. What happens if you start closer to the critical temperature? All that happens is this curve gets shifted like that, and T naught happens later. So this is some temperature T1, this is some temperature T2, which is closer to the critical temperature. So this region lasts longer before you take off. If you're exactly at the critical temperature, you never take off. You just hit the fixed point and stay there. Okay. So this is a way of parametrizing. So it gives you some intuition into how the flow is and what approximations you can make. Okay. So now let's just use this to calculate a correlation length. I'll do that. It's quite easy now, because we're not going to take the complicated situation where it's close to TC and going there, and that's discussed in detail in Wilson's review. In fact, I was going to talk about that, but then I decided that it can get a little confusing. So I decided to take the simpler case where it just goes to the fixed point. Then the results are very simple. So what do we want to compute? So we want to compute these are the correlation functions. Remember, this thing always comes multiplying by delta function, so we're just dividing it out. When you calculate this, you always get a momentum conserving delta function which you can divide out. These things become important because when you do rescaling, you get factors of 2 to the power of d from this. So you have to keep track of that. This whole approach involves doing this constant rescaling so that you're always measuring things in units of the cutoff. So as you do this, you're always going to rescale your p so that p again goes from 0 to lambda. Okay, so it's not going to go from lambda to that, but again to lambda. So you'll always rescale your p. So that's crucial. So so we will do the usual rescalings and write exactly what we did in the discrete case, except now it will be a continuous rescaling. We had the same rescaling in the discrete case. When we integrated half of the momenta, we multiplied by a factor here. But here the interpretation is not half. You integrate it out up to a time t, which means a factor of e to the power of t. Okay? So if you want, what you're saying is at t, if the coefficient of q squared in u2 is 1, and that requires a scaling of t, then at t plus dt, you change this to to maintain 1 as the coefficient of q squared. So this was the normalization, rescaling you did at time t to maintain that coefficient as q squared. Then after integrating out, after moving a distance dt, you change your normalization to that to again maintain 1. So what you've done is you've taken your previous one and multiplied by this ratio. So the ratio this is what has been multiplied at this stage. So this is a factor from 0 till there. This is a factor from 0 to here. So between this stage and this stage, you multiply by that factor. Okay? So for when you changed by an amount dt, you ended up changing the normalization by that factor. Okay? So this is basically 1 plus times dt. Okay. So this is the change in normalization in the step from t to t plus dt. This change is entirely decided by the Hamiltonian at that point, okay, because you're doing the calculations here using ht. So this step is done using so this ht will determine this quantity. Right? Remember the c was determined by the, in our case it was always a factor of 4, but that's in one loop. If you had gone to 2 loops, you would have found some effect. Anyway, this has to be calculated using ht. So this quantity will depend on ht. It will be some function of ht, and we will write it as so this equation has to be solved, where this is obtained by doing the diagrammatic calculation, which we did in our simple example. We didn't have to do it because we only did it to 1 loop, and it turns out this effect starts at 2 loops, so we didn't have to do it. But if you're doing it, you would have to do this. In any case, there's some function v of ht which we don't have to worry about, which gives you this. So this is a rescaling step. And then what is this q prime? Q prime is e to the power of t times q. Previously q prime was 2q, now it's e to the power of t times q. Okay? And as before, 0 less than q will be less than 1. That's always maintained. So now what's the idea? This is what you have to calculate with your h naught. We'll just evolve this over a time period t and use ht to calculate the thing. Keep doing these rescalings. And ht will be approximated by h star. And it doesn't matter what t is, because the result doesn't depend on little t. You can do this iteration 100 times or 1,000 times. The correlation function is not going to change. So you can choose any t to do the calculation. The idea is to choose a convenient t. What is a convenient t? Convenient t is where your h is near h star. Convenient t is when you reached here and gone over there. Final answer doesn't depend on t. So you just put that in. So let's write down the final expression. So I'll write it here. So let's define this quantity. This is something you calculate with your fixed point Hamiltonian, which you can calculate. This we know how to calculate because h star is a simple Hamiltonian. Okay. This is a simple fixed point Hamiltonian. And we know how to calculate with that. H naught may be very complicated. We don't know how to calculate with h naught, but we know how to calculate with h star. So you do this calculation, and now you try to relate gamma to this object. And all there is some rescalings. Okay. So what is gamma? You can easily see that it's Z inverse. This factor comes from, because the gammas have sigmas and this one has sigma primes, so this is factor Cn. And then there's a factor e to the power of minus dt. So this comes from the delta functions. So I told you the delta function gives me e to the power of t. So there's a d-dimensional delta function. So you get a factor of e to the power of dt. That's this. And then there is f star. So in terms of this object, this is your answer. Okay. Now, of course, you say, I haven't calculated anything. You can say, I haven't calculated anything. I've just written it in terms of some expression. But notice that this has a nice scaling form. Okay. Because this guy is decided by this equation, 1 by c dc by dt is v ht. And we're going to put this as v h star. Sorry, what is it?
We are going to choose a coordinate t in which h becomes h star.
Yeah, so if you're starting at some t here, let's say you're starting here, let's say at t equals 0, you're going to go to large T to reach this point. T will be just a large number. Okay. But as I said, the value of T is not going to come in directly in the final result. Okay. So the point is this will be replaced by H star, which is a fixed number. Fixed. These are just full of numbers. You can it's a number, so you can just calculate it. And in Wilson's notations, it's d minus ds. So this c is just e to the power of d minus ds times t. So when I choose t, if I choose t large enough, oh, I've run out of time. I'll just finish this. When I choose t large enough, this will be replaced by that. Okay. So let's write the final expression for t large. And I'll do one more thing and then we'll stop. E to the power of n so this is one result where t has to be taken large enough that you're near the fixed point. But the answer doesn't depend on t, because this left-hand side doesn't depend on t. But to calculate this, you have to choose some t and do it. You choose it large enough fixed point. But the power of this is not that. The power of this is I can now derive a relation between gamma of q1, q2, qn and a scaled gamma of sq1, sq2, sqn. I'll just do that and stop. So this is what is done and usually in all the RG, including when people work in. So suppose I want to calculate gamma sq1 sqn tc. So I've scaled all the momenta by a factor s, and you want to know how it scales. Well, the answer is you can easily obtain that because the result doesn't depend on t. I can just change my t by log s, shift all my t's by log s, and see how much this gets multiplied by. And that will be the answer. So you can easily convince yourself that this just gives a factor of s times d minus because when you shift everything by log s, you get factors of s to the power of this, s to the power of that, and the result is going to be the same. So you'll get this factor times that, times the original expression. Okay? So that's the simple scaling relation you get by assuming that it's dominated by the fixed point. Okay? Now there's some restrictions on what values of Q you can do here, and I'll just say that and mention. So first of all, of course your Q's have to be less than 1, because that is a cutoff. But also SQ, because you're studying the scaling, SQ must be less than 1, because you're using it in that region. But finally there's one more restriction, that QC should be greater than 1. What is this saying? This is basically saying that Q should be much greater than 1 over C, or if you want, C should be much greater than 1 over Q. That means the correlation length should be large enough that the quantities you're measuring are well inside that. What does that mean? That means you don't see that you're away from criticality. The correlation length is so large that your correlations are not going to see it, then for all practical purposes you are exactly at TC and you are at the fixed point. So since we use that as an approximation that we are going towards the fixed point, T close enough to TC, this has to be satisfied. Okay? If you're exactly at TC, this is trivially satisfied. C is infinite. But if it's not, you have to make sure that that is satisfied. Okay, okay, I think we'll run out of time. So there's some, if you read Wilson's report, he does a lot more sophisticated analysis, as I said. He also talks about the validity of this and the various criteria and so on, which I don't have time to do. So I'll stop here. What I want to do next is to talk about what he calls the topology of the RG flow, and in particular the connection with field theory. So so far we talked about critical phenomena with no reference to particle physics, field theory. But all these ideas will be used in defining what is called the continuum limit of a quantum field theory. And so we want to use these ideas to talk about the continuum limit of the QFT. That's what I want to do next. Okay, let's stop.